Today I will speak about the P2P aspect of signature aggregation. I'm Camilo, I'm from Codrivium, and I will present some efforts from our team and also the results of some discussions with EF research team. So let's get started. With post-quantum signatures, really a lot of assumptions that we have today are changing. So basically the size of signatures that we have grows from something like 6 bytes to 3 kilobytes. Also the aggregation size increases to 128 kilobytes. Well, the exact numbers still depend on the scheme that we're going to choose, but yeah, approximately in the order of magnitude, it's how it's going to look like. Also, the aggregation cost increases. So previously, the aggregation cost was pretty low. So basically, any attester in the network could perform an aggregation, and now it's relatively high because we have to perform snark aggregation. And for that, what is changing is that we cannot anymore just simply rotate who is current aggregator within a subnet to perform an aggregation. So there should be some process of selecting the aggregator, and they're going to be basically the members of the subnets who's going to be performing the aggregation. Just some numbers that we considered in our work is that would have something like between 8 to 32K number of validators. So that's basically the amount of signatures that we need to aggregate. Also, we have like now 4 second slots. But the general approach, I think, will be more or less the same. So basically, we have like a two-tier architecture where we first begin with subnet aggregation. So within the subnet, we perform first aggregation, but instead of BLS aggregation, it's going to be snark. We call it just snark 1, and then there's going to be some global aggregation topic where the peers, the global aggregators, would further recursively aggregate these snarks into some global snark, which we're going to put on chain. Of course, that's still a matter of modification, so maybe we'll come up with a better scheme, but that's how we project it so far. And this opens up a certain P2P design space that we consider. Like first is how we perform subnet aggregation. For example, whether we wait for some certain threshold number of signatures that we want to collect before we actually perform the aggregation, or maybe we come up with some kind of aggregators collect some certain number of signatures, then they aggregate them, create snark, propagate it to other participants in the subnet, then they keep updating this snark. There might be different strategies of how we actually perform this aggregation. The next thing is subnet topology. Like again, here we have to kind of agree on some assumptions that we want to choose before we agree on which topology is the best suits for these needs. And the next thing would be kind of how we communicate between subnets, so that once we have subnet aggregates, how we broadcast it to global aggregators, so that we then create the global snark. So for the subnet topology, there are some key questions that really affect how we're going to choose the best topology that we can use. So, for example, whether we can have assumption that validators or aggregators addresses are public. Currently, it's not the case. So basically, because we're using COSIP sub, there is no need to presume that addresses are known. So basically, validators, they just subscribe to subnet aggregator's topic and broadcast their signatures there. Then there is a question whether we need all validators to receive all signatures in the subnet. If we have validators that only perform attestation and they are not performing aggregation, whether it's really needed for them to actually receive the signatures from other participants within the subnet. And the same question, whether the testing validators actually need to receive the subnet level aggregations. Obviously, they need to eventually get the final aggregation, but for the subnet aggregation, there is a question whether they really need it or not. Depending on how you answer the question, we really can choose, I think, the best topology. In our work, we started just as some simple direct topology where just testing validators would create a signature, and then there are some local aggregators inside the subnet their address is unknown, so they just testing validators can just connect to them directly and send their signatures. Then aggregators would propagate it within to other aggregators, and then once they have enough, they generate a snark. The another thing that we obviously need to consider is the gossip sub. It's a well battle-tested topology. Here, all attesters and aggregators, they kind of participate in the same topic, kind of what we have now with PLS, signature aggregation. There are mesh connections where we actually send the signature messages, and non-mesh connections where we send different kind of I want messages to optimize gossiping. With that topology, everyone in the topic would receive a signature, receive aggregation. There is no requirement for anyone to actually expose their public address. Another interesting topology that we think might be also considered is grid. Without going just deeply into details, with grid we can basically it is possible to send any signature from any validator to any other validators within at most 2 hops. So the propagation is really fast. Also, because there are only 2 ways how each individual signature can get from one validator to another, there are really at most 1 duplicate that any participant can get. To make it work, each validator should have the same view of this 2-dimensional lattice of nodes, and for that we need again all validators to kind of be aware of addresses of other validators in the subnet. We can combine it and just take any of these topologies as building blocks and combine them together. Like for example, attesting validators, they can send to aggregators which are connected using grid topology, and then they propagate the signatures to each other very fast. That way we only need to expose public addresses of aggregators, not the validators. So there are a lot of design space here. Once we have the subnet aggregation, this first snarks, obviously because they have weight of 128 kilobytes, it doesn't make sense to just simply gossip them. But instead, it makes sense to kind of just announce that the aggregator actually has a snark. This could be done in the form of a bit field, so that when global aggregator, for example, receives this bit field, he can decide whether he needs this snark or not, depending on whether global aggregator already observed the snark for this subnet, or maybe they now observe the better snark, which aggregates more signatures. The pool topology, I think, is the way here to implement this. So to test all of these assumptions and to implement them, we created a very simple simulator. We just go with the name BeamSim for now. It is a discrete event simulator, so that means it allows us to actually have very reproducible results. We just supply with some seed, and then if we want to repeat the test, we can do this. It simulates real TCP and UDP transport beneath, and it actually horizontally scalable with the number of CPU cores, because NS3 has very good MPI support. So each subnet we can put into separate process and run in a separate CPU core, and only there are not much really between inter-process communication. So only when the final aggregation aggregation is done, only then we communicate with other subnets. So it is available on GitHub. There are instructions how to. It is written in C++. There are instructions how to actually build the project, but if you're lazy to build it, there is a Docker which you can use if you want. It is not as stable. I just checked yesterday. Unfortunately, MPI is not working very stably under Docker environment, but still. You can give it a try if you want. Once you have a project built, it looks something like this Jupyter notebook, where you can basically configure some default parameters for your network, like number of validators, number of local or global aggregators. For example, if you go with gossip sub topology, gossip sub parameters. different well, cryptographic constants like size of signatures, of snarks, like how many signatures we need to collect before we actually perform an aggregation, rate per second, like how many signatures we can verify. Well, how many signatures we can aggregate within a second, how many snarks we can aggregate, and so on. So, and then, yeah, we choose basically the topologies that we want to run, and then, yeah, we can see like how long it took for us to generate the snarks, like the first snarks, and then the global snarks. And once we had like the global aggregators collected enough local snarks, they perform an aggregation, and then we see the exact point in time, like when the very first global snark was produced. Yeah, then we can also check like what was the total network traffic consumed in the network, what was the peak bandwidth for different types of nodes, like validators, local aggregators, or global aggregators. Yeah, I think. Yeah, I really hope this will kind of spark some discussions like about the design, like what we actually want to implement, and check different assumptions. So yeah, if you have any suggestions, feel free to approach me or contact me. Yeah, and that's all I had. Thanks. Dave?
Can you talk a little bit about your different options for simulating networks? Which ones you considered, why you didn't go with the other directions? Because in P2P, right, we're doing awesome stuff, scaling.
Yeah.
I know Giannis is here too, they're doing simulation stuff. There's several options. Why did you go with NS3? Because this is not what the other P2P projects
Yeah, I think that's the most asked question, like why not Shadow? Like here, yeah, the thing is that yeah, with Shadow we kind of the Shadow is great for just taking, like, for example, real client implementation and just simply replacing the system calls, and that way we can simulate the network. The thing is that we run the real binary, and so we basically have as many processes in the network, as many as many nodes we want to simulate. With an S3 approach, we basically run the entire subnet in a single CPU core. So we consider this kind of to be more scalable, and also we don't really need to have a real client implementation to test this. We're only testing the one particular aspect, or just small part of the client, which is the signature aggregation part. So we can really optimize for that. So yeah, in our test we were able to simulate like 5,000 nodes on a laptop. Yeah, this might take, I don't know, maybe depends on the size of the subnet, but for 1,000 nodes it could take like maybe 30 minutes or so. But for smaller subnets, yeah, it runs faster. But still, it's possible to do it in a single laptop. It doesn't consume as much RAM as it would if you use Shadow for the same number of nodes. So yeah, but still it is great, yeah, because we listen to suggestions like Shadow, for example, has this RIPE Atlas database which has the latencies between the nodes from real world, and we parsed this data from Shadow and took it. So in our simulator we also use real world latencies to kind of have the very close environment to the simulator. Also, yeah, we still simulate TCP and UDP transfer, so things like TCP congestion, if we observe them in real network, like if all participants can send their message to one same aggregator, for example, then we might end up with TCP congestion, and our simulator would actually have the same behavior. That's kind of in contrast to something like maybe 3SF Mini. That's well, it checks the algorithm part, but it doesn't simulate the TCP or the networking transport as thoroughly as NS3. So yeah, that's why. But yeah, we are open to suggestions. Yeah, if we can actually try to use Shadow as well. But for now, we thought yeah, NS3 actually makes sense here. Yeah. Thanks. Question. Yep.
So I haven't followed what studies you did, but what are the challenges that you've seen at that layer? Like I don't know, with regard to the topology, the different topologies, or the protocols, or the custom subsettings. Any take-home kind of results?
Yeah, so basically what we observe is that what challenges, well, we basically comparing different topologies. Obviously, the direct topology that I showed previously was the fastest, but again, it's kind of has certain assumptions that we need to consider. We noticed that, for example, Gossip actually runs as fast as Grid for a relatively small number of nodes in the subnet. For example, here we have just 64 nodes, but if this number grows, for the Grid topology, actually if we assume very fast signature verification time, then the time of aggregation stays more or less the same for Grid topology in contrast to Gossip sub, because in Gossip sub we kind of starts having more hops between for communication. Yeah, well, there are still a few things that we need to improve here for scalability of the simulation. We want to reduce like the challenge with implementation was like if we have for example, if we use MPI and we run and we have a lot of between process communications, then this really slows down the simulation. But if we can avoid this, for example, we don't need to put all local aggregators into the same topic so that they don't really talk to each other, but they rather speak directly to global aggregators, then simulation runs much faster. So yeah, we're trying to implement this thing, for example. I don't know, the main challenge is, well, the basic thing is that we have to just agree on certain assumptions, like which topology we should use, and then, with this framework, I believe it's easy to implement and check these assumptions. So we just hope that this would give kind of some tool for cryptographers just to check their assumptions, like if we use, for example, this snark scheme with this verification time, with this snark proof, what effect this would have, like what would be the peak traffic consumption for different nodes, and whether we can afford this for our nodes. Yeah. Yep.
Yeah. Basically, do you simulate the latency like within subnet and between subnets, or just between subnets? What is the assumption here?
Yeah, we simulate latency between any pair of nodes for communication. So we just take the RIPE Atlas database, which has real-world the data for latencies between nodes around the world. Well, it has just around 2,000 nodes, but we extrapolated it a bit in this database so that we have, for our test scenarios where we run, for example, 5,000 nodes, we still can use it. But yeah, we run it. We have latency between any pair of nodes, not only within subnet, but also between subnet to global networks as well. Yeah.
Yeah. Right. Thank you.
Okay, if that's all, yeah, I'll be here, so feel free to approach me if you have any suggestions or questions. So thanks.
Thank you, Camille. We have